everybody. Welcome back to our second attempt at doing a lecture today. If you are not part of the live stream for today, just full disclosure about events that happened. I started the 121 lecture 2.5 hours early because I typed the wrong thing in and then convinced myself that was what I was doing, and I went all the way to like hit the button and people came to lecture and I started lecturing on 121 and someone was like, isn't this class at 2:30? And I was like, is it? And I look up at my thing in horror and it says right here, yeah, 2:30. It's right there. It was noon when I did that, and I was like, I have ruined everything. So thankfully, everything has been unruined due to the efforts and mostly because you guys told me. I don't know how to segue. But we're back, and it is actually the correct time. What do we got going on tonight? Quiz number 5 is due tonight. Make sure you get that in by the deadline. We're going to finish Unit 6 today, probably, so quiz number 6 is going to go up. Last call for quiz number 5 will be tomorrow. And we're going to talk about lab number 3 today a little bit too. So let me go to this screen, but then first I need to get... Oh, I had it out because that was this morning, and then I closed it. So I have to find it again. Hold on. Lab number 3 is a models lab and a naming lab. It's basically a Unit 5 and then the naming parts of Units 4 and 5 exercise. I feel like this would be a good lab that should have been, like, in my schedule, like, if I had put this before the exam, like, it'd be great for reviewing. But at the same time, I can't guarantee that I will have enough time to, like, have the assignment close before the exam. So if you're looking at this and thinking, oh man, I wish I could have studied from this, yeah, sorry about that. But to be fair, it was here. Online here, so. What I have here is a worksheet that is going to ask you to do actually, let me just get this out here real quick for later. It's gonna ask you to construct Lewis structures of molecules. And it goes through the discussion of like how you assign geometry. Like we've all done chapter 5 and we've taken an exam on it, and the quiz for it is due tonight. But you can go through all of these. We'll just get down to the examples here. It talks about polarity and how to name stuff. So down here, I have 10 molecules that I want you to draw on paper to the best of your ability, and then play around with them. Then what I do is I give you a link somewhere in here. I give you MolView. I'm sure I do. Do I? Oh, I give you the molecular geometry simulator. I must be thinking of 131. Okay. We'll just click on this. This is fine. So I believe that I showed this in class once it loads. There we go. We remember this, right? I showed this in class where we played with shapes. So that link for this is in the... Oh, I lost my thing here. Hold on. That link is in the page right here, which you can't see because I have cropped it poorly. There we go. So right here, lab worksheet number 3, PHET molecular geometry simulator. So you can play around with that too. But really, all the worksheet is just draw the Lewis structure of all these things. And then for each of these things, list the following. List the number of electron groups around the center of the atom. List the number, or list the Vesper geometry. List the number of non-bonding electron pairs, and then the molecular geometry. And then is the molecule polar or not? So you're going to have a field that looks like this. Wow, I cannot crop for shit today. Hold on. This is what your worksheet looks like. And you're just going to fill this in for all 10 of them. You do not need to upload a structure. Just draw that on your paper, and then fill in all the answers, and you're good to go. Down here at the bottom are the names. You'll notice that the first 8 are for typing in the name of the formula, and then the last 7 are typing in the formula of the name that it was given in the lab documentation. So you do need the lab documentation to answer all these. So you need to have all of this stuff so that you can do the questions. And then you enter it in here. Be very careful, because I will grade strictly on any sort of typographical error that leads me to interpret your answer as a different molecule. So, for example, if you spell carbonate with an I in it instead of an A and you get carbonite, which might be a thing, like, that would be marked wrong. Like, nitrate and nitrite are 2 different things. So if you do the wrong spelling of something, but I know very clearly what it is, so like if instead of doing like aluminum, you type in aluminum or something like that without one of the I's, or like a very simple type like that, those are okay. I can deal with those as long as I don't accidentally mistakenly interpret your substance for a different compound. Then you're good. Okay. For the formulas, though, you can't type in subscripts. Just type them in to the best of your ability. So, like, if this was your formula, COHSO33, like, do the best that you can. I realize that that's going to be difficult because there aren't subscripts in Google Sheets, and that's okay. I don't expect you to figure that out. That's more or less the worksheet, and that'll be due next week. So please make sure that you have completed that by the deadline a week or so from today. Sorry, I'm just closing Windows here so I can get back to this screen. Oops, I gotta click over here. There we go. Let's put that on the screen real quick. This is where we left off yesterday. We did exercises where we converted particles to moles, and we did exercises where we converted grams to moles. More the second one than the first one. Actually, most of this was done not yesterday, but last week. Wait, was it? Sorry, I'm getting all my days mixed up now. I don't know what it is with me today. 4 hours, not enough sleep. That's what it is with me today. We did all this earlier in Chapter 6. Which day it was, I can't remember at the moment. But I do know that on Monday, when we last had class, we definitely did this discussion where we talked about moles of the big thing and moles of the smaller components in it. So, like, that's the P2O5. So this could be... So in 1 mole of this thing, there are 5 moles of this thing. And you get that from the formula subscripts, which are these numbers right here. So that's where all this comes from. Now, we can put all those things together in a diagram that looks like this. This is straight out of the textbook, but I've recreated it so that it's a little more colorful. This diagram is basically a blueprint, kind of like the blueprints that we've been making all along for any dimensional analysis problem. And as long as you know where you're starting at and where you're going to, you can solve the problem. Now, what are A and B in this? A and B are just 2 different things. So really, the only statement that I need to write is A and B are not the same. So A can be anything you want it to be. and B can be anything else. In other words, if I gave you a question that gave you grams of CO2 and I wanted you to turn it into moles of CO2, the thing that you are looking at is CO2 in both cases. So you are not doing an A to B because it's CO2 to CO2, right? But if I said, I give you this mass of CO2, how many oxygen atoms are in there? Then it would be CO2 versus oxygen. That would be an A to B. If you have an A to B, you have to cross this bridge in the middle. If you don't have an A to B, you just stay on this side. You're going to see various problems that we do. Most of them are going to use this chart where we go across the bridge, but all of the problems that we've done to this point have been just, I have this many grams of carbon. How many moles is that? That's not an A to B because that is just carbon to carbon, right? So you can apply the flowchart to all of the problems that we've already done. Just be careful you don't get mixed up and say, oh, I always have to convert from A to B, because you don't have to always do that. In fact, most of the problems we've done so far, you haven't. So be mindful of that when you are doing these types of problems. Look at what the problem is asking you, and then decide from there what you're trying to solve for. So let's do that together for this first example. I'm going to give you vitamin C. I'm going to give you 250 milligrams of vitamin C, which is just not enough. You should have more. Eat 74 more oranges. In that sample, how many vitamin C molecules are there? Okay, so is this an A to B? Or am I just asking you to do a problem like we'd done before? Well, you can see that. No pun intended. You can see that by, okay, I gave you vitamin C mass. I want vitamin C molecules. Those are the same thing. They're both vitamin C, right? So I need to find vitamin C mass on this chart, which would be here. So I'm going to start here. And I want vitamin C molecules. That would be here. So I'm going to do this. Turn vitamin C grams into vitamin C moles. Vitamin C moles into vitamin C particles. In this case, A is vitamin C, and B is not applicable. If it helps you to write out something like that every time, then do it. A is vitamin C, B is just nothing. We're not using it. And then draw arrows all over the flowchart so you know where to go. So now let's go and write in all the relationships for these, like we've been doing all along. So for grams and moles, how many grams of vitamin C are there in a mole of vitamin C? Well, we can go look that up. How do we go look that up? You find it on the periodic table, or you look it up on Lentech by typing the formula in and getting the mass. I don't remember the volume or the formula for vitamin C, so C6H8O6. So I typed that in on Lentech. I guess we could window capture that, can't we? So, boop, there it is. And so if I type in vitamin C, the molar mass of vitamin C is 176.12 grams per mole. Just in case you don't have Lentech, which you should by now, there's the link to it. You can also just look up molar mass calculator, and it will tell you online. So I'm going to write that relationship down. 176.12 grams of vitamin C equals a mole. And then up here, in a mole of vitamin C, how many particles are there? Well, there are Avogadro's number of things in a mole. So in a mole of vitamin C, there must be Avogadro's number of molecules. Now that we have all those relationships, we can then do our dimensional analysis. So let's do that. I gave you 250 milligrams, which is this many grams. I'm going to cancel this unit out with something. We're going to turn that into moles of vitamin C. And then I'm going to cancel out that unit with something. Let's put that there. We're going to turn that into, we'll go from moles to particles. In this case, we're working with a molecule, so I'm just going to call it that. But if you want to write particles of vitamin C, that works too. It doesn't matter. And then finally, we'll go in and write the numbers. So here, 176.12 grams of vitamin C, 1 mole of vitamin C. Down here, 1 mole of vitamin C, Avogadro's number, molecules of vitamin C. So if I do this calculation, I should get the number of molecules of vitamin C in the sample. So let's punch it in the calculator. I get 8.55 times 10 to the 20. Well, I should just write that down. Molecules of vitamin C. So hopefully that problem will be review for you, because that's nothing new that we haven't done already. You're just turning something from grams into moles and then moles and molecules. That was where we started our discussion of the mole in the first section of Unit 6. All right, I'm going to hit clear so that the text will appear. There was our path that we took, and there's our answer. All right, I'm going to give you another one. I'm going to guide you through this one too, and then after that, I'm going to have you do the problem on your own. So for this second problem, I'm going to give you caffeine. I give you a mass of it. How many grams of that caffeine sample are nitrogen? So, of the things I gave you, the first thing I gave you was caffeine. The second thing I gave you was nitrogen. They're not the same, so I am going to go across this mole to mole connection. Then I just have to figure out where I'm starting or where I'm going. So I gave you a mass of caffeine, so we're going to start here. And I want to know the mass of nitrogen, the number of grams. So we're going to end here. So this is our path. I'm going to turn grams of caffeine into moles of caffeine, moles of caffeine into moles of nitrogen into grams of nitrogen. I'm going to write out the relationships over here just because I'm going to run out of space with those arrows if I don't. So the first relationship we're going to have is grams of caffeine to moles of caffeine. And in 1 mole of caffeine, which is C8H10N4O2, we'll go to Lentech and type that in. I have a really loud keyboard, so 194.19 is what I got. And then for this next one, moles of A to moles of B. So moles of caffeine to moles of nitrogen. Well, if this is my formula, in one of the caffeines, how many nitrogens are there? Well, it's hard to see because I have this line going through it. There are 4 of them. Because of that right there. And then finally, moles of B to grams of B. So moles of nitrogen to grams of nitrogen. In 1 mole of nitrogen, how many grams are there? Well, according to the periodic table, there are 14.007 grams of nitrogen. So we have all the relationships set up. We know our path to get to the end of the calculation. So let's do that. I have that much caffeine. I'm going to cancel it out with something else. So we'll put this in its place. I'm turning grams of caffeine into moles of caffeine. Then I need to cancel that out because that's not what I want either. That's not the answer. There we go. We're going to turn that into moles of nitrogen. We're just following the path right here. And then finally, moles of nitrogen to grams of nitrogen. And those cancel out too. All right, let's fill in all the numbers that we have. So 194.19 grams per mole. In 1 mole of caffeine, there are 4 moles of nitrogen. And in 1 mole of nitrogen, there are 14.007 grams. And we'll punch it all in the calculator and what we get. I got 0.029 grams. There you go. Now that makes sense that the amount of caffeine that I get to start with and the amount of nitrogen contained in it are these numbers relative to each other. I could not have more nitrogen than I had caffeine, for example, right? So there are 0.029 grams of nitrogen in 0.1 grams of caffeine. Which is kind of cool to think about because now you can calculate parts of any substance you want to. All right, so there's our path and there's our answer. All right. So this next problem, I'm going to give you 0.1 grams of adrenaline. And what I want you to do is, following a similar strategy to what we've done, tell me how many atoms of hydrogen are in the sample of adrenaline. So first move, figure out what A and B are, then plot your course through the flowchart, then write out all the relationships, then do the calculation. Okay? I'll give you 5 or 6 minutes to try that, and then we'll go over the answers at the end of that period. See you in a bit. We're going to do 1 or 2 more minutes, so we'll go over the answer here. All right, let's go over all the answers here. So let's do all the setup. So first we got to figure out what A and B are, and I said this in the chat here. So the first thing that you're given, we'll call it A. And then the thing you're solving for, we'll call it B. They are not the same thing, so now we just got to mark where we're going. So I gave you a mass, so we'll start here. And I want to find how many atoms of hydrogen are in the sample, so that would be here. So remember, particles is sort of just a term to use for all of them together. Atoms, molecules, formula units, they're all particles. All right, so now we know our paths. We're going to go like this, then like that, and then like that. So that means I need to figure out grams of adrenaline to moles of adrenaline. So we'll go grams of adrenaline. I'm going to just abbreviate it ADR. How many grams of adrenaline are in a mole of adrenaline? Well, according to Lentech, and I didn't look this up during the break, but I should have, that is 183.20. Okay. And then we can go moles of adrenaline to moles of hydrogen. And for every mole of adrenaline, how many hydrogen do I have? I have 13 of them. Because in one of the molecules, there are 13 of the hydrogen atoms. And then finally, moles of hydrogen to particles of hydrogen. H is atomic, so I'm going to write atoms instead of particles. And in 1 mole of anything, there are Avogadro's number of that thing. So we got all the terms written out. Let's do the dimensional analysis. So I've got 0.10 grams of adrenaline. We're going to cancel that out and turn that into moles of adrenaline. Oh, we'll do the numbers later, actually. Let's just do all the units first. Then I'm going to cancel this out with this down here. We'll turn moles of adrenaline into moles of hydrogen. And then same process here. There you go. And so now we'll run the numbers. So in a mole, how many grams were there? Well, 183.20, because that's what we wrote down here. In a mole of adrenaline, how many moles of hydrogen are there? So one of these, there were 13. And in a mole of hydrogen, there are Avogadro's number of anything. There you go. Punch it on the calculator. What do you get? I got 4.3 times 10 to the 21. So it looks like your answer for the moles of hydrogen, that looks pretty close to the right answer. But it looks like you stopped here and you got to do this last step. So multiply whatever number you got in the calculator by Avogadro's number and you should get my number. But it looks like you're really close. All right, so now you know how to find the number of moles in various samples. And you can then turn that into grams or atoms or whatever is asked of you. Where'd my cursor go? There it is. All right, I'm going to give you sugar. This is table sugar. This is what you put in coffee or sprinkle on, I don't know, toast? I don't know what you use. I don't use sugar on anything. I use it for baking and cooking and stuff. So I'm going to give you 0.522 grams of it. First, I want you to tell me how many particles of table sugar are in that quantity, how many moles of oxygen are in that quantity, how many grams of, I didn't underline that one, grams of carbon, and how many particles of hydrogen, particles being atoms. All right, so this is a lot of problems, so I want you to try at least 2 of them before we go over the answers. I'm going to give you 10 minutes to do this, because there are 4 of them, and it's a long process. And then we're going to go over all of the numbers together, and then we'll take a break. All right, go ahead and practice, and let me know of any questions in the chat, and I'll be around to answer them. So see you in a little bit. All right, 1 or 2 more minutes, and we'll go over the answers to these. All right, let's go over the answers. I went a little long there, but that's okay. That's the wrong thing. There we go. We'll do those 2 first. And of course, that glitches out. There we go. All right. I'm going to grab something real quick. Hold on, actually. So let me go back to this screen. And I'm going to go like this. Boop. And then we'll go like this. Boop. And then I'm just going to cut this and paste it. Oh, crap. Hold on. That's no good. Paste. There we go. Ah, why is this happening? Why is this a thing? Sorry, hold on. There we go. All right, so for the first one, okay, I definitely don't want to draw over this, so we'll just do that. There we go. So for this first problem, I give you a mass of sugar. So for all these, oops, I need to select the pen, not the drawing tool. Okay, or yeah. For all of these, the first thing that you're going to look at is sugar. And then B is going to depend on which problem we're looking at. So for the first one, how many particles of sugar? We have that. So what that means is that I've given you a mass of table sugar, so all of our problems are going to start here. And then it's just where do we end from there? So this first one, we're going to end here. So this is our path. And so let's write down the relationships. So there's some number of grams of sugar in a mole of sugar. And we can look that up on Lentech if I had it open still. Where is it? There it is. $342.30 is what I got. That's not PowerPoint or Photoshop, whatever. There we go. So that many grams of sugar in a mole. And then I know that in 1 mole of sugar, there are Avogadro's number of molecules of sugar. So let's do the dimensional analysis. I gave you this many grams of sugar. Let's try that line again. There we go. I'm going to cancel that out with down here. So grams of sugar. We're going to turn that into moles of sugar. And then I'm going to cancel moles of sugar out with molecules of sugar. And then we'll run the numbers. So in 1 mole of sugar, there are 342.30 grams of it. And in 1 mole of sugar, there are Avogadro's number of particles. So I can compute the answer, punch it into the calculator here. And the result I get is 9.18 times 10 to the 20 molecules. So in half a gram of sugar, there are 9 with 20 zeros after it molecules of sugar. That's ridiculous. There's a lot of sugar. Molecules are small. All right, that was the first one. So pause the video if you need to record that, because I'm going to go like this. Boop, and everything I just wrote is gone, but that stays there because I made a layer. All right, now we're going to figure out moles of O. So in all of these cases, A is going to be sugar. But depending on the problem we're working on, B is going to be something different. So in this one, B is oxygen. And because I have a mass of sugar to start, and I'm asking you for moles of oxygen, I must be going to this spot right here. So now we can write out our relationships, and I'm going to write them down here. So this relationship we're just going to use every time because we're always going to go from grams to moles. So 342.30 grams of sugar equals 1 mole sugar. So now when I erase everything, those things will just stay there, which will be kind of nice, right? All right. Then I'm going to turn moles of sugar into moles of oxygen. So moles of sugar, moles of oxygen. Okay. In a sugar molecule, how many moles of oxygen are there in a mole of sugar molecules? How many moles of oxygen are there? Well, according to the formula, there are 11 oxygens per molecule. So in a mole of molecules, there'd be 11 moles of oxygen. And that'll tell us how many moles of oxygen are in the sample. So let's go do our dimensional analysis here. And there you go. So we'll set up our units just like we did before. And then we'll put in the numbers. 1 mole is 342.30 grams. And in 1 mole of sugar, there are 11 moles of oxygen. We punch it in the calculator. And get the answer, 0.0168. There you go, that's the second one. We'll just do that. All right. I am going to need the formula of sugar because I'm going to keep forgetting it, so I'm going to write it down up here. There you go. That's just handy for us to have. All right, let's do the next problem here. We'll just keep everything here that we need. So the next problem, how many grams of carbon are there? So B is going to be carbon. I know it looks really stupid saying B equals C, but that's okay. We already did the first relationship to get us from grams to moles here. I want grams of carbon, so we're going to do this. We got the first step already taken care of. You always do sig figs. Anytime you do math, do your sig figs. In 1 mole of sugar, how many moles of carbon are there? Well, according to the formula, there are 12. And then finally, moles of carbon to grams of carbon. 1 mole of carbon is 12.011 grams of carbon. Is the 11 in moles of oxygen 2 sig figs? No, because it's counted. So these numbers right here, this is counted. So this is exact. So that's not going to affect your result because you can count the number of oxygens. It's exactly 11. I see the issue, yeah. So that doesn't affect your sig figs, but all the other numbers do. So you should still have 3. All right, let's do the dimensional analysis. I got to kind of cram it in here a little bit more now. So I think it was what? 522 grams of sugar. Then we'll turn grams of sugar into moles of sugar. We'll turn moles of sugar into moles of carbon. And we'll turn moles of carbon into grams of carbon. And now we'll just run the numbers. So this is still the same as before. This is always going to be the same for all these problems for that first step. 1 mole of sugar is 12 moles of carbon. 1 mole of carbon is 12.011 grams of carbon. But yeah, this number is exact. And when I do that, I get 0.220 grams of carbon. So of our half a gram of half a gram of sugar, almost half of that sample is just the carbon. The rest is the other elements. And then similarly, I'm clicking on the wrong window here. You could do this for hydrogen. I gotta get rid of that, so there we go. And now I want particles of hydrogen, so I can go in this direction. We'll write out the relationship. So we've got the sugar grams to moles. 1 mole of sugar is 22 moles of hydrogen due to the number in the formula up here. And 1 mole of hydrogen is Avogadro's number of atoms of hydrogen. And then we'll go set up the problem in exactly the same way. I'm going to abbreviate sugar now just because. We've written it so many times here. And then, again, we'll run the numbers. We're just using the relationships that we've got right here. And punch it on the calculator. What do you get? 2.02 times 10 to the 22. All right, there you go. There are all the problems. I went way past break time, so we're going to immediately take a break. When we come back, we're going to balance chemical equations, which is something totally different. So we'll see you for that in about 10 minutes. Get the music going again. Where is it? There we go. Alright, we're back. Let me wind our Meridia music down. Alright. This next section, we're going to talk about chemical equations, which means we're finally going to actually do real chemistry on the screen to show how chemistry occurs when you mix two things together. So, we're going to do actual chemistry. We're going to write equations on the board. We're going to use these reactions to understand what's happening in our reaction vessel when we mix the things together. Now, this is going to be really useful much later in the class when we start talking about like gases, that's Unit 7, equilibrium, that's Unit 9, and stuff like that, for figuring out what's going on under specific conditions. And we can say, oh, well, this reacted with that, and so this is a base, and thus da-da-da-da-da-da-da. So that'll be Unit 10, and then that's going to sort of tie into biological systems that you're going to see in cell bio and so on. So we've really only discussed equations and chemical reactions sort of in descriptive terms, like qualitatively, more or less. So one such reaction that I might have said, which would have been near the beginning of the quarter when I dropped or showed the videos that dropped metals into water, would be something like this. Sodium and water react vigorously to form sodium hydroxide and hydrogen gas. That's a good description of what's happening, but can we be more specific? Like how much sodium is needed? How much water is needed? Do I get multiple products of anything? Because it turns out that you do, if we consider everything at the atomic level. First, we're going to write that as a chemical equation. It looks like this. Now, where did this equation come from? How did we get these numbers? We're going to go over that in this section. We're going to talk about how to balance it, what all those terms mean, and so on. So, the first thing that we're going to do is we're going to label the sides of the arrow. The left side of the arrow, or the tail end of the arrow, are the reactants. Reactants are things you react together, and they go on the left, generally speaking. Now, if I flip the arrow around, they would go on the other side. They're always on the tail of the arrow. But in nearly all cases, we write our reactions left to right. There will be a special circumstance where we write reactions backwards, sort of. And we'll talk about that in Chapter 9. Well, if reactants are things you react together, then what do we call what you produce? We call it products. Oh, might sneeze. Sorry, hold on. Oh, sorry. Sometimes I sneeze like 3 or 4 times in a row. You don't want to hear that. You don't want to hear me sneeze in the mic. Oh, excuse me. All right. Products are what you make from the reactants. Products go on the pointy end of the arrow at the head. Again, most of the time that's going to be on the right side. Oh, I gotta drink more water. Excuse me. I'm gonna have to get up and blow my nose, actually. I'll be right back. Just a second. Let me put this next slide up on the screen and we'll talk about it when I get back. Sorry about that. My Kleenex is in the other room. I don't have any in the office here. All right, on the screen, you can see that there's a little label after each substance. So I've got sodium and then parentheses S. I got water and then parentheses L. And then A, Q, and G, and all that. These are what are known as the phase indicators for our substances. And they basically state what we're looking at, solid, liquid, or gas. Now, AQ is sort of a special one. What AQ means is that our substance, as written, dissolves in water and then splits apart. So NaOH, whenever you see AQ, that means that this substance will split into whatever ions are shown here, and then they're each aqueous too. Now, this only works if the compound is ionic. If you see something like CO2 aqueous, CO2 will not split into C's and O's because CO2 is covalent. So you do need to know which substances are ionic and which are covalent, based on what we talked about in chapters 4 and 5. You're going to notice that as we go through these chapters now, we're going to be recalling a lot of stuff from previous chapters, because this is all going to start building on itself. We've done all the basic stuff. Now we're in the advanced stuff. So that means we're going to need to refer back to all the things that we've done. All right. Now, how do you know if something is aqueous or not? That depends on whether it is soluble. If something collects at the bottom of your container and just sits there as a solid, you would write solid. But if you put something in there like table salt, stir it really well, and you see that it disappears, then it dissolved, it's aqueous. Things that dissolve and you no longer see or observe them are aqueous. All right. Lastly, we have a bunch of numbers here. You'll notice that one of my arrows here is pointing at a blank. There's no number there. That number is implied to be 1. The number is used to balance the equation. The objective of balancing your chemical equation is to ensure that you are obeying the conservation of matter. What is the conservation of matter? The conservation of matter is a statement that says any matter you start with, you must also end with. So I cannot create or destroy matter. In other words, if I'm doing a reaction and I have 2 hydrogen atoms for my water, I cannot end with 3 hydrogen atoms for the hydrogen and then the sodium hydroxide here. So here I have just 2. I can't end with 3. So I have to put these numbers in here so that everything multiplies out so I get the same before and after. If I didn't have these 2's in here, I'd be creating hydrogen when I did this reaction, and that's not allowed because that's not what actually happens, right? We're going to spend the rest of this section learning how to balance chemical equations so that we can use them for later calculations. All of the stuff that we did earlier today in the period where we did mole to mole, mole to gram, etc., using that table, we're going to do that again using these chemical equations that you see on the screen here. But first we need to be able to balance them. So whenever we are doing a chemical reaction, all of the pieces have to be used, and you can't throw any extras away. It's like a puzzle. You have to use all the pieces in the box or the puzzle is not complete, and you can't add other pieces to the puzzle because they wouldn't fit. So in a chemical reaction, our job is to figure out how many pieces there are, not what the end picture is or whatever, because that I'm going to give to you. I'm going to say, this reacts with this to make that. Balance the equation. So it's really important that if we're going to be using these equations for anything, like to model what's going on, to do a calculation, we have to have it balanced, because if it's not balanced, you're going to get an invalid result. So always check to make sure your equation is balanced. First thing, look at the equation. Is it balanced? If it's not, you're going to get the wrong answer. If I give you an equation that is already balanced for you, you should still check it anyway, but odds are it's fine. If it's not, I need to know. Sometimes I will give you an equation that is unbalanced, and then I will just put blanks in there, and it's your job to balance it, and then do the equation. So let's do some exercises where we balance equations. I'm going to just skip over this because that's just telling you what we're going to be doing. I'm going to show you what we're doing. So to balance an equation, first we need to prepare some blanks here for numbers that we're going to put in front. Then what we're going to do is we're going to split the equation right down the middle into products and reactants. Oh, excuse me, I had to sneeze again. Once we've done this, we can now count up the number of atoms on each side. So I'm going to first just index them. So I got a carbon, a hydrogen, and an oxygen. So we're going to go carbon, hydrogen, oxygen. Those same elements live over here too. And we're going to take inventory. How many carbon are on the right? Or I'm sorry, we're going to start on the left. How many carbon are on the left? Just 1. How many hydrogen are on the left? 4. How many oxygen are on the left? 2. And then we'll do the same thing on the right side. How many carbon are there? 1. How many oxygen? 2. How many hydrogen? Oh, sorry, hold on, I messed up. How many oxygen? Well, there's these 2, and then there's this one. So there's actually 3. And then how many hydrogen are there? There are 2. All right. As you can see, when I do this reaction as written, I have destroyed hydrogen and created oxygen. That's not allowed. We cannot throw away 2 hydrogen atoms and then gain an oxygen atom if these are the only things that are going into the reaction. That won't work. So what we need to do is we need to put numbers in those blanks so that we balance the equation so everything has the same numbers on both sides. So I'm just going to pick a number for an example. I'm going to do this. I'm going to pick 2. I'm going to put a 2 right there. If I selected 2 for that spot, what changes? Well, now I have twice as much hydrogen. And I have 2 oxygens plus these 2 oxygens, which would be this. Now, I just arbitrarily picked a number. You should pick numbers that help you balance things out one at a time. So you'll notice that my putting a 2 there was actually pretty good because now the number of hydrogens that I have is good. My carbon was already good, so putting a number in either of these spots would not be very useful to me. I gotta put this blank back because I erased it. So plan ahead when balancing equations. Look at what you need to match up and then put a number there and see what happens. Most of the time what will happen is that you'll put a number down and that will make you want to put a number somewhere else, and that'll make you want to put a number somewhere else, and then you'll be done. It'll just work out. That's most of the time. Not all the time. Sometimes if you make a mistake, the numbers can get out of hand. We'll talk about that in a little bit. So now that I'm at this step, I need more oxygen. I only have 2 over here. I need 4 on both sides, but thankfully it comes in 2, so if I just do this, then now I have twice as much oxygen on this side, and my oxygen is balanced, and thus this is the reaction that happens. So if I burn 1 CH4 and 2 oxygen molecules, I will make 1 CO2 and 2 water molecules. And this is the correct reaction because the reaction is balanced. So that is your objective. I want you to balance equations by entering numbers in before the molecules. All right, and so this is just me doing that. I'm going to give you another one, and so I'm going to put the blanks down. And what I want you to do is balance this equation following the same strategy that I just did. This one's a little bit different because there are fewer products, which seems like it should be easier, but that can actually become a little bit obnoxious. So play with it a little bit. Type in your answer in the chat to the best of your ability. And we'll go over the answer in about 4 or so minutes. One more minute, we'll go over the answers. All right. Let's see what we can do here. All right, so we only have two elements here, nitrogen and oxygen. And then we're going to count them. So I got one nitrogen, and then I have 1, 2, 3 oxygen. Over here, I have 1 and 2. Now, this reaction kind of forces you to put a number in this spot first. Where'd my cursor go? Oh, there we go. I have to work here first, because if I put anything on the other side, I would increase the amount of oxygen I have, which would get me further away from the correct answer. However, there's no real number that you can add there. Excuse me, that fixes this, because oxygens come in pairs, right? So I'm kind of stuck with just putting a 2 here and seeing what happens, right? Which, unfortunately, not super useful. Like, this isn't going to help me get to the answer until we say, oh, I need 1 more nitrogen and 1 more oxygen here. So if I put a 2... Why does my cursor keep disappearing? There we go. If I put a 2 there... Oh, it's because my mouse is on the edge of the thing. That's what's going on. I gain 1 of each, and now both are balanced. And there's the result. 2NO plus O2 makes 2NO2. All right, and then my little guide is going to go through that too. There you go. Now, as we do these reactions, you're going to encounter situations that will have very common themes. Like you'll see polyatomic ions, or you might see something reacting with oxygen. And there are some tricks that you can use to help you. So the first thing is, if you see polyatomic ions like this, just write them in your inventory as a polyatomic ion. You don't really have to worry about the charge because we're not balancing the charge. Just drop them in there, and that'll save you some effort. That can help a lot if you have stuff with like extra oxygen coming around or whatever. When you're working with a molecule, generally speaking, do the most complex things first. Do the simplest ones last. This is the most important. Notice how we were always doing oxygen last in these reactions if we touched it at all. That's because there's only one element. If you get down to a situation where all you have to do is modify oxygen and you have O2, then it's easy. But if you get to a situation where you only have to modify carbon, and carbon is in C6H12O6, you're kind of stuck, right? Then you have to do the whole thing over. And so that leads us to this. Balance elements by themselves, and hydrogen and oxygen last, because they tend to be the simple ones. Finally, if you end up with giant numbers, like you have what's called the like chemistry arms race, where each side the numbers just get bigger and bigger and bigger and bigger and bigger and bigger, and they never seem to balance out. So like numbers higher than 50, erase everything and just start over, because what's happened is you've probably made a math error. Usually the math error will resolve itself when you recount, but sometimes you overlook something, and that will just keep going and going and going and going and going. And the only answer to that problem is just erase everything and start over. So I'm going to give you a bunch of these to try here. I do have one more suggestion to make, and that is that for many reactions, you can link two of the numbers together. For example, this number is going to depend on what this number is because that's where the iron ends up, right? And not only that, but you should have half as much iron on this, or half as much in this number as you do here, because this 2 is going to take that into account. So if I put a 2 here, this has to be 4. And that could help you plan ahead. Same thing with this one and let's get a different color here. Same thing with these two. So this number is going to be linked to this number. And so whatever this is going to tell you whatever should go here. And so I've actually already balanced the equation for you without even doing an inventory, because I know I have to have the same amount of iron, so that solves this. And I know I have to have the same amount of oxygen, so that solves that. So you can start to get to the point where you do these without actually doing inventory. So you don't have to do the inventory if you don't want to, but it is a sure way to get you to the correct answer. So try balancing these equations. I will put the answers on the screen. We'll go over them at the end, and then we'll call it a day. So I'll give you about 6 minutes to do this. So see you in a bit. I just realized we're kind of low on time. I'm going to write the answers here on the board just so you have them. I'm not really sure if you need me to go over these, but I can definitely do that if you need me to. Let's see here. I'm just going to balance them real quick. So, 2, 2. I've done this for so long that like I know what to look for in these reactions. There you go. It's basically what I've told you, but I can do it really fast because I've done it forever. So there's all the solutions. Anything that doesn't have a number in front of it is a 1. If you have any questions, you can let me know. I'll hang out for a bit, and then after about 2 minutes, we'll just do concluding remarks. So there's your solutions. Let me know in the chat if you want me to go over any of those specifically. Last call for questions. All right. If it looks like we're good, then I think that that's all we have for today. So when we come back next week on Tuesday, not Tuesday, sorry, I'm thinking of the morning class. When we come back next week on Monday, we're gonna finish Unit 6. We're gonna do some more calculations, then we're gonna move into Unit 7, which is the ideal gas law. And so we'll talk about that next time. Make sure that you get quiz number 5 done by tonight. It is due. That is a soft deadline. The last call will go out tomorrow over email. And also make sure that you start working on lab number 3. Lab number 3 is going to be due next week. I will post the announcement or the assignment on Canvas, and you will need to have it done by next week as well. No quiz for next week currently because we didn't finish Unit 6 today, so that's fine. Yeah, that's all I got. Have a wonderful weekend. It's going to be nice and sunny. Go out and enjoy some rays.